Yeah, it's broken. I have a pencil.
So what we're going to look at today is what if the beam, gravity, and the rope are not all nice 90 degrees to each other? Or the short version of that, torques at angles. Except this first question that I appeared to want to start with is actually a very difficult question. So even though I called this example 1, I'm looking at this and I'm going, this should have been like example 3 or 4. But this gives you an idea, Shashan, of what we're going to be looking at today. What if your torque is slanty? What if the rope is slanty and gravity is straight down? So what I want you to do is look at the second, well, the page over. There are 2 main types of beam problems that are slanty. Where the beam is still perpendicular to gravity, the beam is horizontal, and only the rope is slanty. Those, I can't call them easy, those are easier. Where the beam and the rope are slanty, like this right-hand diagram, and at different angles, those are pretty tough. Doable, but pretty tough. In all of them, though, our strategy is going to be components, 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 and what we're going to always want to try to find is the component that's perpendicular to the beam. Put the phone away, my friend. For the remainder of class, face down. Thank you. So to solve them, we're going to apply the 2 conditions for equilibrium. We're going to say the sum of the forces is 0, the sum of the torques is 0, and we will usually put our pivot point right by the hinge that's mounted to the wall. So as an example, really you want to look at example 2 on the next page. It says, find the cord tension and the hinge force. Okay? Find the cord tension and the hinge force exerted by the hinge on the beam. Generally, when they give me a beam, it's a torque question, and I'm going to start out either labeling my forces or with a free body diagram, but I've learned over the years it's usually, unless the diagram is nice and big, and this diagram is not nice and big, it's usually worth redrawing the beam and labeling everything carefully, because Gianluca, that also helps me not miss stuff. So I'm going to start out by saying, here's my beam. Nice and long, big. What are the forces acting on this beam? Get the obvious ones. Where am I going to put the gravity force on a beam? What did we say last day? Do you remember? Center of mass. So I'm going to call right here M beam, MBG. What other forces? Look at the diagram, think, what other forces? Tension? Like that? I don't like that. That's one we're definitely going to componentize. What else? Sorry? Yeah. How about I call that MLG? Because it's also a force of gravity, but it's the mass of the load times G. Let's break tension up right now, by the way. So tension is going to be broken up into tension perpendicular and tension parallel. Also, how big is that angle right there? 30 degrees. How big is this angle up here? See the Z? Let's put a little 30-degree angle in there. That can't be it. Why can't that be the only forces on this system? Pardon me? Well, notice which way is tension parallel exerting a force? What direction? To the left. Are there any forces to the right now? Then this couldn't be an equilibrium. So the wall itself, the hinge, the wall itself, I think it has to be exerting a force to the right. And not only that, I'm pretty sure I know exactly how big that force to the right is. It's exactly the same size as which force in my free body diagram? Parallel. Yep. Okay. Now, I'd like you to use your imagination for a second. Do not write this down. I'm going to muck up my diagram. Temporarily, I'd like you to use your imagination and imagine the, don't write this down, imagine the pivot right there. Just imagine it. Now, why did I do that? Because, Rob, how far is tension from the pivot? What's its physical distance? Say 0. How far is the mass of the load times G from the pivot? So how much torque will these two guys exert? 0. I can temporarily ignore them. Now, if the pivot was there, this still would not be able to spin. As I look at it, though, the only force that I see here is this mass of the beam times G. If the pivot was here mathematically, this would cause it to spin. Well, that's impossible, then it couldn't be in equilibrium. There has to be some other force counteracting that. I'm pretty sure not only is the wall pushing to the right, I'm pretty sure that hinge is also pushing up. Otherwise, this system cannot be in equilibrium. Let's get rid of that pivot. Nathaniel, you see how I reasoned my way there? I said this because two things have to be the case. The forces left have to be forces right, forces up have to be forces down, but also torques clockwise have to cancel out torques counterclockwise no matter where you put the pivot. That has to be the case if it's in equilibrium. Now, I'm not going to put the pivot on the end on the right-hand side. I am going to put the pivot, and you can draw this one in. I am going to put a pivot right there. That's going to be where I'm going to pretend things are rotating from. Why? Because there's two forces that I don't know right there. How far are they from the pivot if I put the pivot right there? 0. How much torque will they exert? None. In fact, Fy won't exert any torque. Fx, it didn't matter because it's parallel to the beam. It's not going to exert any torque at all anyhow. But let's get rid of Fy. And now we're going to start out solving this with torques. And little advice, you're probably going to want to draw a line right down the middle of your page, because on the left-hand side, we're going to find tension. On the right-hand side, we're going to do the second part of the question, which is find the force on the hinge. So on the left-hand side, we have this. Is there a beam? There is? Then I always start out by saying the sum of all the torques clockwise in this direction has to cancel out, has to equal the sum of all the torques counterclockwise in that direction. So looking at where I put my pivot, which forces would cause this thing to spin clockwise in this direction? Fx can't, it's 0 distance from the pivot, and it's parallel, it won't exert any torque. There's my pivot. What would cause it to spin this way? MBG, what else? Okay, but not just the forces, torque, which is force times distance from the pivot. So what I'm going to write for the left-hand side of my equation, the mass of the beam times G times its distance from the pivot plus the mass of the load times G times its distance from the pivot. How far is the mass of the beam's center of mass from the pivot point? Well, how long is the beam? 0.82. So where's the center of mass going to be? 0.41. And how far is the mass of the load from the pivot point? That's the mass of the, I want the distance from the pivot. 0.82. It's on the end of the beam. What if it wasn't on the end of the beam? They'd have to give me one more measurement so I could subtract. They'd tell me how far it was from the end or something. There's all my clockwise torques. What about counterclockwise in this direction? Which force is exerting a torque counterclockwise in this direction? Tension, again, good, perpendicular, not tension. We don't look at slanty forces. Tension perpendicular. Times its distance from the pivot. How far is it from the pivot? 0.82. And what I'd like to find, Brett, is tension perpendicular. Use that to find tension, and I think I can because I got a lovely trig triangle up there. How would I get tension perpendicular by itself? Okay, so we're going to have this. Tension perpendicular equals mass of the beam. 9.8, 0.41 plus mass of the load. .8, 0.82, all divided by 0.82. Try this on your calculator. Brackets around the top. Double check my typing. 0.22 times 9.8 times 0.41 plus 0.7 times 9.8 times 0.282 divided by 0.82. I think I'm right. Do you get 7.938? Yeah. And since this is not my final answer, I'll carry a few extra sig figs. That's the perpendicular component. How can we find tension? Well, it's part of a triangle, and I've learned over the years it's worth quickly redrawing the triangle here. So what we have right now is this. 7.938 parallel tension 30 degrees. Which trig function will I use to find tension if I know tension perpendicular? Well, tension perpendicular, opposite, adjacent, or hypotenuse. Tension, hypotenuse, that's adjacent. Which trig function? Sine. So we end up with the sine of 30 equals 7.938 over tension. Yes? How do I get the T by itself, tension by itself? So 7.938 divided by sine 30. Most common mistake, because this is, you don't find, all year long, we haven't found the hypotenuse very often. We've almost always been finding a component. So the most common mistake I see is kids go, oh, 7.938 times sine 30. Remember when you cross multiply, things move diagonally. The T would move up there, and the sine 30 would move down there. Yes? With me, Graydon?
Yeah.
Okay, because you were drooling a little bit there. 7.938 divided by sine 30. What's the tension in the rope? $15.9. Okay. That's the first part of this question. First part said, find the tension. Done. Only took one whole page. What else did they want us to find? Okay. That second part, the hinge force, that actually makes this a really challenging, a more challenging, an even more challenging question. Okay? We can't directly. What we can find is Fx in my diagram. What did you tell me? I think it was you. What did you tell me Fx was the same size as? Someone said parallel. Can I find parallel? I think so. Okay? Then we're also going to try and find Fy. We'll see if we can figure that out. And then what we're going to do is we're going to add those two together, tip to tail, do the Pythagoras, do the trig, and that is the angled force that's coming off that hinge. Does that make sense? It's a lot of work still. Well, let's make a little note here. So Fx equals tension, not perpendicular, parallel. Let's go back down to my triangle. Which trig function could I use to find tension parallel? Yeah, I could use, I'm going to use tan just in case I got this wrong somehow. I'm going to be confident that I got the perpendicular right. I'll use tangent. Tangent of 30 equals perpendicular over parallel. Tan 30 equals 7.938 over parallel. Going to be divided by tan 30 again, yeah? 7.938 divided by tan, divided by, didn't go, Mr. Duke, divided by tan 30. I'm getting 13.75, which is not my final answer, so I'll carry a few extra sig figs. 13.749 if you really want to. Yes? No? 13.749, and that equals also the horizontal component from that hinge. Has to, because those are the only two horizontal forces. Okay. Any suggestions on how I could find Fy from that diagram up there? Is it equal to MBG? I think, Brett, you had a suggestion.
Add up MBG, add up LG, and then subtract.
Oh, see, he's actually saying F up everything has to equal F down everything. So you're saying Fy and perpendicular tension has to cancel out both the masses. Yes, because that was the first condition that I gave you 2 lessons ago of equilibrium. If something is in equilibrium, the sum of the torques is 0, torques clockwise equals torques counterclockwise, and the sum of the forces is 0, F up equals F down, F left equals F right. So, if I hear you correctly, and I think I do, you're saying Fx plus perpendicular equals the mass of the beam times g plus the mass of the load times g. Sorry, not Fx, Mr. Dueck, Fy, Fy, Fy. Make that x into a y. Silly. Yes? How would you get Fy by itself? How would you get Fy by itself? So Fy is going to be, what was the mass of the beam? 0.22 times 9.8 plus 0.7 times 9.8 minus 7.938. How big is Fy? .22 times 9.8 plus 0.7 times 9.8 minus 7.938. This is going to be small. A little worried it was all going to cancel. 1.078. No? Yeah? It's exactly half of MBG? Probably because the mass of the load is on the very, very, very end, so I suspect the tension in the rope and the tension on the hinge are splitting the whole thing, but yeah. I don't think I would always just assume that, though. It depends on where that load is, and often it's not on the end. Okay. Oh, that's not what they wanted either. Here's what they want. 1.078 plus 13 point, what was it? 749? This is the force of the hinge. There's a lot of work for one question. These were about These and momentum collisions at angles really, well, no, I guess the potential energy putting something in orbit took a lot of work too. These are long questions. Let's do the Pythagoras. This squared plus 13.749 squared square root 13.8 at, and let's find an angle theta, running out of room here, opposite, adjacent. Shift tan of 13.749 divided by 1.078. I'm running out of room to show all my work. You get an angle of 85.5 degrees off of the wall. I don't know how we would quite write that. To the right of the wall. To the right of vertical. That hinge is actually almost pushing straight up. It is pushing to the right just a little bit, but 85 degrees, that's nearly vertical. That's how we're going to handle torques at angles. Nathaniel, you give me a rope at an angle, all components. It gets tougher when you give me both a rope at an angle and a beam at an angle. That gets a bit tougher in terms of I really have to get tricky with it. Like example 1, can you turn back to the very, very first page? Yep. Example 1. Says the beam below has a mass of 12 kilograms and a total length of 8.5 meters. If the beam is in equilibrium, what's the tension in the rope? This is a bigger diagram than the last one. It's already taking up most of the page, so I'm not going to bother redrawing this one. I think I'll label this one, Courtney, as is. Hey, what are the forces acting on this beam, folks? Get the obvious ones. And I'm going to draw it nice and big because I have a feeling I'm going to be using it as part of a triangle. In fact, I'm going to tell you what I'm going to be doing pretty quickly here. Vlad, I'm going to break this up into MG perpendicular and MG parallel. Parallel down the beam will exert no torque at all. Perpendicular is what's exerting a torque. What other forces are acting on this beam? Tension. Is that perpendicular to the beam? No? Then we better go components. Tension perpendicular. Tension parallel. How big is this angle right here? How big is this angle up here? This bottom one, a little trickier. Ready? Watch. How big? How big up here if this is 90? 55, yes? What do these two also add together to form? So how big is this guy? There, I found a way to get that 35 into my triangle. That's a 35 as well. Well, that's what we did with ramps. This is the reason I'm doing this question. This is reviewing forces on ramps where we broke it up into perpendicular and parallel, and we did notice, oh, that angle down there became that angle up there. But we just kind of memorized that shortcut. I re-derived the proof that we did very quickly. This can't be it. First of all, is tension also pulling to the left as well as up? Look at the rope. Is tension pulling to the left as well as up? Are there any forces pushing to the right anywhere in the diagram? I am pretty sure that this hinge is exerting a force to the right. But Vlad, since it's right on the pivot, I don't care. I'll label it, but it's not going to influence my torque. And is this beam sitting on the ground? Then there must be a normal force. Or you could call it an Fy if you wanted to as well. The ground is pushing up. But, oh, how far is that force from the pivot? 0, so what do I care? No torque. I labeled it because I'm a nerd and I wanted everything to be in my free body diagram, but it's not going to affect my calculations.
On the last diagram we did put Fn instead of Fy.
Pardon me?
On the last diagram we did put Fn instead of Fy.
Which way was the surface in the last diagram that we did, vertical or horizontal? Vertical. You can make an argument actually that Fx was a normal force because normal force is always 90 degrees to the surface, right? A wall pushes sideways, you could call that a normal force, I guess. And the floor pushes straight up, that's a normal force. You know what? There I go with X and Y because it's confusing. We didn't do a wall as a normal force very often. Is there a beam, Brett? You know what that means? That means that the sum of all the torques clockwise has to equal the sum of all the torques counterclockwise. Has to. I think I'm going to put my pivot where they have the pivot. Don't have to, but I think this case it'll be much easier. All right, looking at my perpendicular forces only, perpendicular components only, what would cause it to spin clockwise? I heard someone say it, they're right. mg perpendicular. So in my equation, it's going to look like this. mg perpendicular times its distance from the pivot. I'll figure that out in a second. Are there any other forces that would cause it to spin clockwise? Because these two won't exert any torque because they're right on the pivot point. You know what? Just that guy. What would cause it to torque? What forces would exert a torque counterclockwise? Tension perpendicular times its distance from the pivot. Okay. How far is the mass of the beam from the pivot, center of mass? Where did the 4.25 come from? Oh, they told you the length of the beam in the actual question? So 4.25. And how far from the pivot is tension perpendicular? Careful. 8. Right? It's half a meter from the end of the beam. 8. Oh, and I forgot to put a perpendicular on my tension. My bad. For what it's worth, how would I get the perpendicular component of tension by itself? I'll divide by 8. But you know what? I got a problem. I got a component on the left-hand side. I don't have mg. What did I write instead? mg. Let's redraw that. Well, let's do the trig. I got that triangle. See it? Opposite, adjacent, hypotenuse. Yes? Which trig function can I use to find the perpendicular component if I know mg? Show. Cos. I'm going to have cosine of 35 equals perpendicular over mg. I could cancel out the m's. I don't want to because I want to actually keep my m in my equation, so don't cancel out the m's. What I want to get this by itself. How would I get that by itself? Times, okay, this is the key. This is what I wanted to get to. So if I hear you correctly, Cole, and I think I do, you're saying wherever I see mg perpendicular, that's the same in this diagram as mg cos 35? Let's go stick that into this equation. It's going to be mg cos 35. one of the most common mistakes here, Chase, kids get the trig and they're so proud. I got the trig, it's coast 35. They forget to drop the 4.25 down. The number of times I've seen them write the distance in the first line and forget to drop the distance from the pivot in the second line. It's amazing. Equals tension perpendicular, which is what we're trying to find, and then we'll find tension. How would I get the perpendicular by itself? What will I do with that 8? Right. I hit the perpendicular is going to be, what was the mass of the beam? I've scrolled down. What was it? 12 times 9.8 times cos 35 times 4.25 all divided by 8. Times 9.8 times cos 35 times 4.25 divided by 8. You get 51.1765. I'll carry some extra sig figs. I'll go 1765. Sure. Because that's not what they wanted us to find. Alejandro, what did this question want us to find? Read the question. What does it say? Find what? Tension. We've only found perpendicular. But look. I got a triangle up there. Let's see. Here's the 40. Perpendicular, opposite, adjacent, or hypotenuse. Tension. Hypotenuse. Which trig function? Sine of 40 equals perpendicular over tension. I guess that means that tension equals perpendicular divided by sine 40, 51.1765 divided by. By the way, you'll notice in this question, Emily, we used cosine at one point, yes, and we used sine at one point. You also may notice I'm being way more careful with my trig. I'm sometimes redrawing triangles. I'm certainly labeling stuff really carefully. I'm writing out the whole equation. I'm cross-multiplying, then plugging stuff in, because you're going to find in this, more often than not, you've got more than one trig function going along. Too easy to get confused. .6 newtons. .6 newtons. Now that I knew that, could I find some of the other forces? Could I find Fx? Could I find Fy? Sure. Except I'd have to start over. I'd have to somehow find horizontal and vertical components of tension. Because I found perpendicular and parallel to the beam, but I haven't done anything with gravity. This would be a tough question. I could do it. Meh, not gonna. There's a whole box there, isn't there? Yeah. The one that was sitting right next to it? I brought it this morning just for you guys. Okay? Example 3. So when the beam is not horizontal, the problem becomes more complex, since we often need to consider one set of components for torque and a different set of components for the force equations. Example 3 says, find the chord tension and the hinge force. Finding the hinge force here, this would be a scholarship question back in the old days. If the beam was flat, wouldn't be a scholarship question. That's fair game. If the beam's at an angle and the rope's at a different angle, like this, this is going to be a lot of work. And in fact, you know what? Here's what we're going to say. Look up. Go like this. We're just going to find the tension. We're just going to find the tension. And I can tell you from experience, even though this diagram looks really big to you guys, it's going to be too small, and you have lots of room on this page. To the right, draw yourself a nice long beam. Trust me. We are going to put the pivot right there. What are the forces acting on this beam? Get the obvious ones. Okay, mg of the beam, so mass of the beam times g. There's also mass of the load times g. What else? Tension. Is tension pulling to the left as well as up? You know what? I'm pretty sure the wall then is pushing to the right. And for what it's worth, the wall is also supporting some of the masses. But since both of those forces, which both would have perpendicular components that I could find, since both of them are zero distance from the pivot, how much torque are they going to exert? So who cares? Let's component the other stuff. So there's going to be mass of the beam G perpendicular and mass of the load G perpendicular. There's also parallel components. I didn't even bother writing those because parallel down the beam is not going to exert torque, and I know from experience this diagram is going to get really lots of labeling and things, so I'll leave stuff off if I can. Is that okay, Grid? Ready? Watch my argument here. How big? 28? How big? 62? Not 72, right? Don't forget to carry the 1. How big? 28? Because they also add to 90 up there. So here we go. That's 28. And I think the same argument can be made for this triangle up here. They're similar, they're identical triangles, yes? Okay. This is the other reason I redrew the beam, is I knew I'd be mucking up my original diagram. How big? See the Z? How big? 55. Let's label that. So let's add the perpendicular component here. Perpendicular. And this is 55 degrees. Is that okay, Rob? And you may notice, Akemi, I'm going slow. The setup is everything in a torque question. If you get the setup right, then the rest of this is really SOHCAHTOA, right-angled trig, and some cross-multiplying. With a vengeance, but cross-multiplying. Now we use our imagination. Is there a beam, Dylan? Say yes. That means that the sum of all the torques clockwise in this direction equals the sum of all the torques counterclockwise in this direction. What torques would cause this to spin clockwise? I think both the masses, yes? So it's going to look like this. The mass of the beam G perpendicular times its distance from the pivot plus the mass of the load G perpendicular times its distance from the pivot. How long is the beam? The question does say somewhere. 7, so center of mass is going to be 3.5. Oh, the load's not quite at the end. How far is the load from the pivot point? Not 7. 5 point. Oh, the load is on the end. 7. Tension is not on the end. Ah. Thank you for reading the diagram correctly and preventing me from making a mistake. Speaking of tension, I think tension perpendicular is the counterclockwise torque times its distance from the pivot, which is, now I agree, 5.9. Do I have two components, Shashan, on the left-hand side? Do I have two components sitting there? Say yes. Do I have, ready, Shashan? On the left-hand side of my equation, do I have two components sitting there? Say yes. I'm going to have to do some trig. Now, here's the nice thing. Shashan, do you agree with me? These two triangles are basically identical in that I know the hypotenuse and I'm trying to find the perpendicular. So whatever trig function this one ends up being, this one will be the same trig function. So let's do this one here. Adjacent hypotenuse, which trig function? But be very careful. Let's see. This is going to be cos 28 equals perpendicular over neither. I want to get this by itself. How would I get that by itself? Okay, so if I hear you correctly, Shashan, and I think I do, what you're saying is over in this equation, instead of that perpendicular, I can go mass beam G cos. Don't forget to drop down the distance. Plus mass load G cos. Don't forget to drop, include the angle, Mr. Dueck. Don't forget to drop down the distance. And how would I get the tension perpendicular by itself? Can I do that on this line? Because now it's going to be plug and chug. I've scrolled down. What was the mass of the beam according to the question? Let me change colors first of all. 12 times 9.8 times cos 28 times 3.5 plus, what was the mass of the load, please? 8 times 9.8 times cos 28 times 7, all divided by 5.9. What's the answer? Well, 28, Mr. Dueck. Twelve times 9.8 times cos 28 times 3.5 plus 8 times 9.8 times cos 28 times 7 equals, divided by 5.9. I get tension perpendicular is 143.726. Tension perpendicular equals 143.726, which isn't what I wanted to find. Jimmy, what did the question say that they wanted us to find? Find the chord what? They didn't say perpendicular, did they? Okay, we're nearly done. Looks like I have this. Perpendicular. There's tension. What was this angle? 55 degrees, yes? Where there's my 90? Jimmy, my friend, tension perpendicular, opposite adjacent or hypotenuse. Here's my angle. Tension perpendicular, opposite adjacent or hypotenuse. Yeah, I'm making you wake up. My bad. I definitely agree this is hypotenuse, but I'm pretty sure opposite. Yes? Yes, 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 yes? Jimmy, redeem yourself. Which trig function has the O and the H in it? Not that's A and H. That's cosine. Which trig function has the O and the H in it? Oh. Which one, folks? Sine. Wake yourself up, my friend. A little more coffee. Perpendicular over tension. So I think tension is going to be perpendicular. Yeah, no, it looks like sine SS. These are my 5s. Divided by the sine of happy. You have no idea how tough that is for a lefty. That's easy. That's what you stupid righties do. Man, no wonder your handwriting is neater than mine. Jeez. I got perpendicular still stored on my calculator, divided by sine 55. And I get 175 newtons. $175 newtons. Okay. This, by the way, had I been giving you a test, this would have been B+ level question.
What would the mark break down?
1 mark for writing torques clockwise equals torques counterclockwise. I would give you 1 mark for this line here. I would give you 1 mark for putting in the correct trig functions, so we're up to 3 now. 1 mark for finding perpendicular, that's 4 marks. I would give you 1 mark if I saw that there. Sorry, if I saw that there, 5 marks. 1 mark for the answer, 6 marks, and probably 1 for the free body diagram or something like that. Yeah, it was a good mark. The nice thing is, they were tough to get 0 on because every kid memorized, oh, if I write the torque thing down, he gives me a mark. If there's a beam, I write, but you get to know your stuff. Okay. Turn the page. Pardon me? I don't know. Okay. Turn the page. It says, consider the diagram below, the beam below. What will be the direction of the vertical component of the hinge force Y? I think I've already told you it's got to be that one there. And the reason is, if you imagine the pivot right here, you have nothing preventing this from turning clockwise or counterclockwise. You need some equilibrium force. Okay? It actually, you know what? I take that back. It depends on how big this is. If that was really, 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 really heavy, then force Y would actually have to be pulling down to prevent it from causing things to spin. It depends on the mass. What's your homework? So from the great big equilibrium review package, I gave a couple of torque questions. Okay? You can either jot these down or I'll wait for a couple of seconds for you to find the equilibrium package, the ultimate equilibrium review assignment. I will be collecting this. This will be the last assignment I'm collecting. I'll make it worth like a free 30 or 40 marks or something nice to bump up your grades or whatever. No torque on your final exam. Okay? So, here is what I think you can do. Write this down or circle these questions. I added number 8. This is very, very similar to example 2, where you have everything horizontal except the rope at an angle. The rope is actually tugging away to the right. A little tricky. I already assigned number 9 last day. I already assigned number 10 before. I already assigned 13, 15, 17. And then 20 is asking you to find the horizontal force, FH. Oh, really what you're going to need to find is the parallel component of tension, because they're the same. Remember that? 26. So what have I assigned from this grand total? You ready? I assigned, you can write this at the very, very top if you want to. I've assigned number 1, 2, 6, 8, 9, 10, 13, 15, 17, 22, 25, 26, 28, 29, 30, and 34. The answer key is online showing all my steps. Look there first, because for most of you it's going to be one key step and you'll have that aha moment before you ask me for help.